Hey guys, welcome to another video. Today's learning objective is to identify and interpret roots, intercepts, turning points of quadratic functions graphically, and to deduce roots algebraically. As usual, feel free to skip to any part of the video. There'll be kind of a few worked examples in this. But yeah, let's get on to it. Prerequisite knowledge that we do need is kind of remembering what quadratic functions are, or kind of what quadratics are. So just as a quick reminder, there's something like x squared plus say 5x plus 7, and as kind of you also do want to know how it'd be quite useful to remember how to factorize them. So as a kind of a quick reminder, kind of you think about what number multiplies to give you say the 7 and what adds to give you the 5 as the kind of quick reminder. But yeah, let's get on to it. So you know how kind of we've been talking about straight lines so far. Well, you've also got something kind of in the graphical space, right? So you've got this graph. You also have kind of quadratic functions, which come in the form of, say, y equals that, which is obviously a bit more complex than just simple straight lines. And to think about what they might look like, let's kind of just consider the most basic example of y equals x squared. Okay, so well, when we see a function that we've kind of never seen before, the first way we can approach it is just plugging in values and seeing what happens. So you can make it like a little table. You can say x, y, and then say 0, and 1, 2, 3. So if x equals 0, y equals 0. X equals 1, y equals 1. X equals 2, y equals 2 squared, which is 4. And then 3 squared is 9, and then so forth. We can try say 4, and then that'd be 16. If we have say 5, that's 25. But let's also try negative numbers, because it's if we've got this kind of right hand side quadrant done, or at least the kind of the first quadrant and the second quadrant perhaps done, we do need to consider the third and fourth quadrants. So let's kind of create another table. So you can have say minus 2. Or actually, let's start with minus 1, minus 2, minus 3, and then minus 4. Well, since it's x squared, right, minus 1 squared is just 1 because it's kind of the negatives cancel out. And then minus 2 squared is minus 2 times minus 2. But the two minuses multiply by each other just become positive. So that's 4, and then 9, and then so forth, kind of with the same logic. So if we kind of start plotting these, kind of basic. So we have 0, we have 1. So this is just a sketch, so you kind of see what it looks like. It doesn't have to be perfect. That's what's kind of important to remember. We can have say. So actually, let's move 1 to here, maybe, and then 2 to here, 3, 4, and kind of 5, and then we can do the negatives as well. So kind of just very sketch-wise. I'll show you a proper one in a second. So then kind of we know 0 goes here, 1 goes up here somewhere, 1, 1, and then 2 is kind of 4. So this is 1, 4 is going to be somewhere up here, right? We can do the same thing here, and then 3. So 4 is here, it's going to be kind of more than double, so somewhere up here. And then same thing with the negative 3. So kind of the negative 4s won't even fit, 4 and negative 4 won't even fit in. So kind of let's just join the lines, and then kind of we have no reason to suspect that it's going to be, we should have a straight line joining the points, since kind of we've just done kind of random numbers, right? Like 1, 2, 3, 4. There's no reason, for example, that there should be a straight line here, and since we have no reason to believe that, it's a safe assumption to say it's going to be a curve. So what you can do is kind of, if we go, and then kind of, okay, that's not doing well, and then kind of just a curve to join these up. So that's just kind of like what, as a brief sketch of what a quadratic might look like. It's not a very good sketch because of kind of this whiteboard pen marker thing, but this is just a rough sketch. And whenever you see a function you don't know what's going to look like, you can just plug in some numbers and think about it. And as you can see, what's interesting here is that kind of the y is never going to be negative. And to be honest, we should expect that because it's y equals x squared, right? And whenever you square a number, you always get a positive output. So this is kind of an interesting property. And so if we look at a graph plotter, we can see it here a bit better. So this is y equals x squared, and this is kind of what quadratic function looks like, with this kind of, I guess, a happy face. So the shape of this curve is called a parabola. That's the actual name for it, or I refer to it as like a smiley face, for example. But yeah, and then you can also kind of have quadratics as we've seen before, in forms like this, for example, where you have a term in x and a constant term, so we can just plug that in. So we had x squared plus 5x plus 7, and that kind of looks like that, for example. That's just another one. We can try kind of another one. Y equals, say, I don't know, minus 7x squared plus, I don't know, 234. Oh, that didn't look too nice. Let's say 12x plus 45. So you can kind of zoom out to see it. So that kind of looks like that, which is kind of a negative parabola. It's the same shape as this, but flipped around. So I'll go get rid of that. And then, but yeah, that's kind of it with the quadratics. That's kind of what the general shape is. And then there's some kind of interesting things to note as well. So if I kind of think of a simpler parabola. Okay, so we've got this parabola, for example. What we have here are kind of, it intercepts the x-axis 2 times. We can see kind of intercepts the x-axis once here and here. And so these are called the roots of the quadratic function. Kind of with the straight line, we might have called them the x-intercepts. These are kind of more, in quadratic terms, are more commonly referred to the root. And we've got the y-intercept here again. But we've also got this kind of point here. So before, you can see kind of the value of y is declining as x increases. So x is increasing and y is declining, right? It's getting more and more negative. It's getting smaller and smaller and smaller. And suddenly, at this point right here, at 0.5, the curve decides that it's going to start becoming positive again. Oh, sorry, increasing as x increases now. And this is called a turning point because kind of the gradient here is decreasing. Not sorry, the gradient here is negative, as you can see, with y decreasing as x increases. But then the gradient here becomes positive. And the turning point, the point itself, the gradient here itself is actually 0. And I think we'll talk about more about that in the future. But just as a note, the turning point, you can see why it's called the turning point. It's as x increases, it's initially negative, getting more and more negative. But now, as x starts to increase, y also starts to increase. So kind of the direction of the curve effectively changes. So it's called the turning point. And what you need to be able to do is kind of identify these algebraically. Sorry, not algebraically, graphically on a curve. So the 3 things we need are roots, the intercepts, kind of that's just the y-intercept, and then the turning point, as we talked about just now. So let's kind of do this, one of those really quick. We'll come back to this. So this question asks us to use this graph, use the graph of y equals 2x squared minus 2x minus 4 to estimate the coordinates of the y-intercept, the roots of the quadratic, and the turning point, and to give you answers to 1 decimal point. So let's go in, let's zoom in a bit. Okay, so let's do the y-intercept first. That was the first thing on the right. So y-intercept, again, that's where it intercepts the line, or the quadratic function intercepts the y-axis. So let's just zoom in. I guess I'm a bit lucky because I can zoom in. You might not be able to do this in real life, but that looks like it goes through minus 4. So we can say that the y-intercept, we have to remember give it in coordinate form. So we can say A, well, x is 0. Remember the x-axis, look, it's at 0. But y is at negative 4. And so remember it says coordinates, so we should give it in this form, the coordinate form. B is the roots of the quadratic. And again, the roots is just another way of seeing the x-intercepts. So if we can zoom in. Oh, and remember it said 1 decimal place. While kind of, minus 4 is it's exactly minus 4, but it did offer to 1 decimal place. So what we ought to do is actually write, so you actually ought to write, say, 0.0, and then minus 4.0, just because it does specify in the question. The roots of the quadratic, again, another way of saying the x-intercept, so we zoom in. that looks like 2 to me, so that's one of them, and the other one looks like -1 to me. So let's zoom out again. Okay, so we said 2, so 2.0, remember, because we want decimal place, 0.0, and -1.0, 0.0. And kind of, so for example, this is the y-intercept, right? So the x is going to be 0, the x-coordinate, and for the roots or the x-intercepts, the y-coordinate is going to be 0, as can be seen here. So that's, you kind of should expect that. And now the turning point. This can be a bit harder to identify sometimes, just in terms of just looking at it and seeing where it decreases. So sometimes it's worthwhile bringing the ruler and then kind of working the ruler on it upwards, I guess, in a way. I can't really demonstrate with a ruler, but let me just make a straight line. So you kind of, if this is your ruler, yeah, you can kind of just ooh. So let me select it. Okay, it's not going to do that. Okay, let me try again. So if this is your ruler, then you'd kind of move up and up and up in a straight line to see kind of where I guess like where it stops falling. So the turning point is going to be the lowest point here, as you'd expect. So you kind of work your way up, and then you can say, okay, it's, and then you can draw a line. So you draw a line to kind of like that. This pen's a bit thick, so that looks like -4.5 to me, I think. And then if we kind of work our way up, that looks like 0.5 to me. So we can say C is 0.5 minus 4.5. And that's kind of how you identify those three graphically. It's just really important to sometimes get a ruler out and like kind of have these dotted line and work their way up. It also shows you're working sometimes to the examiner, just in terms of kind of just being a bit safer. But yeah, these are kind of fairly straightforward in the sense that you just have to remember what each of these words means. So kind of y-intercept, the way you can remember it's kind of y-intercept, so intercepting the y axis then, it doesn't say the word axis in there, but you can just think, this is y, so it intercepts that. And then you can remember the turning point because it's kind of intuitively, it's the point, where it turns. So from that word you can remember it. The roots might be a bit harder to remember, just kind of, you've seen y-intercept, you've seen turning points, so the only other points of interest, I guess, are just the x-intercepts, so you can just say kind of those are the roots now. But that's kind of what there is to it. Sometimes they might just give you, say, something like this, and then you have to plot and then kind of do the, find the values of the turning points, etc. So let's do this. With the approach for this is kind of, you can work each out kind of in this table. So for the -2, you work out the values, etc. You do that. And what you can also do is on your calculator, there's like this table function, which lets you put, say, put this function in, this y equals -x squared plus 3x plus 5, that function in, and you should get kind of, they'll kind of give you, say, oh, what's the step? So the step here is 1, because that's kind of between these two, and what's the range? So the range is between -2 and 3. You kind of put those, values in, and it should give you kind of a table with this output. So just try that out on your calculator. But if you can't, or kind of your calculator doesn't do that, you can always do this kind of the old-fashioned way. And here it's just important not to make mistakes, especially with the minuses. Those can trip you up. So first one, you can say kind of, I like doing the working on the side. So we have, so what, y equals minus, so we have -2 as x, so x equals -2. And we have y equals -2 squared plus 3 times -2 plus 5. And writing stuff out like this, it can be a bit tedious, but it makes sure you don't make those silly mistakes. Of course, if you're comfortable doing it kind of mental math wise, give that a go, But don't think this is too tedious or anything. If you want to do it, like, go for it. 4, so -2 squared becomes 4, and then the minus side stays, so -4. 3 times -2 is -6 plus 5. So that's -10 plus 5, which is -5. And then we can fill that out here. -1 is a bit easier to do. -1 squared is 1. And then there's a minus sign still here, so -1. Then -3, because it's 3 times -1. So -1 minus 3, -4, plus 5, -1. 0, kind of the easiest one to do. 0 plus 0 plus 5 is 5. 1, again a bit easier, so we can do the mental math again. 1 squared is 1, so minus 1 plus 3, 4, 4 plus 5, 9. Okay, 2, okay, we can try that. So minus 2 squared is, 2 squared is 4, 4 times minus 1 is minus 4, so minus 4, plus 2 times 3, which is 6, so that becomes 2, plus 5, 7. And then 3, so minus 3 squared is minus 9. Minus 9 plus 9 is just 0, so and then plus 5, which is just 5. So we can try plotting this. Minus 2 is minus 5, so that comes to somewhere here. Minus 1 is minus 1, so that's roughly there. This is kind of, it isn't the best graph paper. A lot of time in the kind of exam conditions, they'll give you a bit, with graph paper with kind of more of these lines, so it's easier to mark up. But at 0, that becomes 5. 1 is 9. And 2 is 7. And then 3 is 5. Okay, so since they kind of give you this table, you really only need to plot within that range. You can kind of predict where the rest is going to go, which is actually a fair enough thing to do. But you kind of, since they'll give you a graph with only kind of that's only so big, so that kind of limits how much you need to extrapolate. Extrapolate just means that after the points you've calculated, just assuming or kind of guessing where it's going to go. But yeah, so let's just join the points. Remember, it's going to be a curve. An important thing to do is, like, if you want a smooth curve, use like the natural curve of your wrist. So like if this is the paper, you can turn the paper and use kind of that motion. It looks a bit weird on camera, but just try it out next time you draw a curve. I can't really do it too well here, but so you'd have something like something like that. Oh, that's quite bad. It's quite badly drawn. It's quite important to have a smooth curve and that goes through all the points. They kind of do actually have marks on this, and not to have like lines like this or like that. So that's actually pretty bad. So I'll kind of redo it. So what I'll do is actually I'll kind of start from here. But what's a lot easier if you do it in one motion. Yeah, kind of the white. This doesn't really help, but so yeah, and then you've got this. What you can't really necessarily do is, I just assume that that's the turning point here. That's not necessarily true. For example, and if you want to check that, you can plug in, 1.1. So minus 1.1 squared plus 3.3 plus 5, which is kind of certainly larger than, so minus 1.1 squared, that's 11 squared, kind of, that's how I think of it, and then you can work with the zero, so that becomes 1.21, so minus 1.21 plus 3.3 plus 5, which is going to be greater than 1 plus 3 plus 5, because you're adding the 0.3 here, and then you minus the 0.2, so the kind of actually continues to go up for a bit, and then down. So an important thing to do is not to assume kind of the largest number here is the turning point. The turning point can very well be after this point. So don't kind of make it turn downwards there. Like just get it to go a bit further and then have it turn downwards, kind of as in the turning point. If you're also kind of estimate this, a lot of the time, what they'll give you is kind of a nicer equation than this, where kind of one of the x's will actually be your turning point. But yeah, so that kind of just depends. So this is a quick way to check, for example. And also you can find the turning point algebraically, kind of for higher tier students, which I'll get to in the next video. So that's how you do this graphically. The kind of learning objectives also deduce roots algebraically. And if we remember what the roots are, right? Let's just go to an example here. The roots are when kind of it's the x-intercept, right? And the x-intercept, we know, is when the y-coordinate is 0. So we have to find that value of x for which the kind of the equation of the quadratic equals 0. So if we go to say the quadratic is, for example, y equals x squared minus x plus, minus 56. And we had to find the roots. So remember, the roots are the points at which kind of the values of x for which y is 0. So we say 0 is equal to x squared minus x minus 56. And we have to solve this equation. So I'll be talking a lot more about how to solve quadratic equations like this in a later video. But it's kind of a quick reminder, I guess, or maybe not a reminder, but kind of a quick preview now. Well, the key is you factorize this. And if you remember our technique for factorization, we have to think of a number which multiplies to minus 56. So AB equals minus 56 and adds to minus 1. A plus B equals minus 1. Since I set the question, I know the answer is this factorizes to x minus 8 and x plus 7. And this equals 0, right? So what values for which this thing on the right will equal 0? Well, if x equals 8, well then you get, for example, if x equals 8, well, let's write x equals 8. So then we have, on the right hand side, you have 8 minus 8 times by 8 plus 7, which is equal to 0 times by 15, which is 0. So when x is equal to 8, that's one of them. That's one of the roots. So one of the roots is 8, 0. And another root, well, if x equals minus 7, this bracket here will come out to 0. And 0 times anything is just going to be 0. So it doesn't matter what this bracket's going to come out to. So let's just check that anyways. So if it's minus 7, well, we have minus 7 plus 7. So actually, wait, let's do it in the order that it says it up there. We have minus 7 minus 8 times by minus 7 plus 7, which is minus 15 times 0, which is just 0. So you have to kind of, with factorization, when you have it in this form, you can just think about, if this bracket comes out to 0, then the whole thing will be 0 because it will be 0 multiplied by some number. And same thing with this bracket. So the two roots are 8, and when x equals 8, and the other one is when x equals minus 7. And that's how you do it algebraically. There's a few actually other methods aside from factorization where you can find the root. That's not algebraically. So they're going to be kind of the quadratic formula, which I'll talk about again in a later video. And for higher tier students, completing the square, which should be actually in the next video. So that's how you kind of deduce the roots algebraically. And if you were, for example, had to find the y-intercept, again, you just plug in x equals 0, right? And then that will evaluate to 0, that will evaluate to 0, and then you just have this. So kind of the constant term is still the y-intercept. So algebraically, it's pretty easy to find the y-intercept. A bit harder to find the kind of x-intercepts, or the roots, and a bit kind of even harder to find the turning point, and that's only, you only need to find the turning point by algebra if you're doing higher tier. But yeah, so there was quite a lot covered in that video. There are a few different things. So it's quite important that you kind of go out and practice. A lot of the time, kind of these questions with kind of plotting stuff, I know they trip me up a lot because kind of it really required you to kind of mark things on properly, to draw the curve smoothly, which takes a lot of practice. So the more practice you can do on this, the better. But yeah, so hopefully that all made sense, and I'll see you guys in the next video.